You think electricity is a flow, a kind of invisible fluid moving through wires, power leaving one place, arriving at another, like water in a pipe. That picture feels simple, too simple, because the moment you ask what exactly is flowing, your confidence starts to collapse. You imagine electricity as a thing, a substance, something you can point to, the way you point to water or air, but that picture was built for convenience, not truth. You flip a switch and the light turns on instantly, so you assume something traveled from the wall to the bulb and made it happen. That assumption feels harmless. It isn't, because almost everything you think electricity is, what moves, what doesn't, what carries energy, what a wire is actually doing, is built on a mental picture that physics does not fully respect. You think the wire contains the action, you think the current is the story, you think electrons are doing what the light is doing. This is wrong, not slightly wrong, wrong in the way a child's drawing of a city is wrong, recognizable, useful perhaps, but not the structure underneath. The water in a pipe illusion, you think electricity flows, not metaphorically, literally, a kind of invisible substance moving through wires, power leaving the outlet, traveling down a cable, arriving at the light bulb, like water through a pipe. This picture feels natural. In fact, it feels so natural that most explanations of electricity quietly rely on it. We speak about current as if something is flowing. We draw diagrams showing arrows moving through wires. We talk about electricity being sent from one place to another. Even the language encourages the illusion. Voltage pushes, current flows, resistance slows it down. The analogy feels complete, but it hides a problem, because when physicists look closely at what is actually happening inside a wire, the picture begins to unravel. The electrons inside a metal conductor are not waiting for your switch to be flipped. They are already there, billions upon billions of them, packed inside the metal lattice, moving randomly long before any circuit is connected. When you flip the switch, you are not releasing a stream of fresh electrons that rush toward the bulb. Nothing like that happens. The electrons inside the wire barely move at all, not fast, not even moderately fast. In many ordinary circuits, the average drift of electrons is slower than a crawling insect, millimeters per second. Yet when you flip the switch, the light turns on almost instantly, not after several seconds, not after minutes, almost immediately. If electricity were truly like water flowing through a pipe, the delay would be obvious. The electrons would need time to travel from the switch to the bulb, but that delay does not appear. The effect happens far too quickly. Something about the water in a pipe picture is misleading. It is not completely wrong. The analogy is useful for basic reasoning about circuits, but usefulness is not the same as truth. And the deeper you look, the more the analogy begins to collapse. Electricity is not a fluid moving through wires. The wires are not pipes, and the electrons you imagine racing through the circuit may not be the main actors in the story at all. The shockingly slow electrons. You imagine electrons rushing through a wire, fast, restless, carrying energy from the outlet to the device. It feels intuitive. If the light turns on immediately, something must have moved quickly from the switch to the bulb, so you picture electrons speeding through the metal like tiny projectiles. But when physicists measure the actual motion of electrons in a wire, the result is deeply disappointing. They barely move. In a typical household wire carrying current, the average drift speed of electrons is incredibly slow, not meters per second, not even centimeters per second, often just fractions of a millimeter per second. Imagine a crowd slowly shuffling through a hallway. That is closer to what electrons are doing. They are constantly bumping into atoms inside the metal lattice. Their motion is interrupted again and again. Any net movement in one direction happens at a glacial pace. Yet the moment you flip a switch, the light turns on, almost instantly. If the electrons themselves were responsible for delivering energy to the bulb, the delay would be obvious. Electrons starting at the switch would need to travel through the wire, inch by inch, until they reach the filament. At millimeters per second, that journey would take minutes. But the bulb does not wait. The moment the circuit is completed, energy begins arriving. This is the first serious crack in the mental model, because it reveals that the electrons you imagine doing the work are not actually transporting energy across the circuit in the way you think. They move, but they move slowly, much too slowly to explain the immediate response of electrical systems. Something else must be transmitting the energy, something that spreads through the circuit almost instantly. The electrons are involved, but they are not the messengers carrying power from one end of the wire to the other. They are part of the mechanism, But the story of electricity is happening somewhere else. The light that turns on. Too fast. You flip a switch. The light turns on. It feels immediate. So immediate that your mind quietly assumes something must have traveled from the switch to the bulb in that instant. Electricity moved, energy arrived. The circuit came alive, but pause and think about the distances involved. In a house, the wire between the switch and the bulb might be several meters long. In larger systems, it could be hundreds of meters. In power grids, it stretches for kilometers. If electrons were truly carrying energy from the switch to the bulb, they would have to travel that entire distance. But we already know how fast electrons drift inside a wire, millimeters per second, slow enough that you could watch them progress with the naked eye, if you could see them at all. At that speed, the light should take minutes to turn on, but it doesn't. It turns on almost instantly. So something else must be moving through the circuit at a much higher speed, something that spreads across the wire nearly as fast as signals travel through space itself. To understand this, imagine a long row of dominoes standing upright. When you push the first one, the last domino falls almost immediately, but none of the dominoes traveled across the room. Each domino only tipped over a tiny distance. What moved quickly was not the dominoes themselves. It was the disturbance moving through the row. Something similar happens in an electrical circuit. When you close the switch, the electrons in the wire do not rush from the switch to the bulb. Instead, they all begin to shift slightly, almost simultaneously, along the entire length of the wire. Each electron nudges the next. The motion propagates rapidly through the conductor, even though the individual electrons barely drift. But even this domino analogy is still incomplete because it suggests the energy moves inside the wire, and that assumption too will begin to collapse. The invisible fields around the wire up to now, you have been looking inside the wire. That is where you expect the action to be, electrons moving. Charges pushing each other forward, energy traveling along the metal, but this focus on the wire hides something far more important, because the real activity of electricity does not stay inside the metal at all. It spreads around it. Every time electric charges move, they create something that cannot be seen, but can be measured everywhere around them, an electric field. And when those charges begin to move through a conductor, another structure appears alongside it, a magnetic field. These fields do not sit inside the wire like water inside a pipe. They expand outward into the space surrounding the conductor. If you place a small compass near a wire carrying current, the needle turns, not because something inside the wire touched it, but because the magnetic field around the wire reached out and influenced it. And the wire is not containing the phenomenon, it is shaping it. When you flip a switch, a change in the electric field begins spreading through the circuit, not slowly like the drifting electrons, but quickly, a ripple moving through space along the wires, reorganizing the electromagnetic fields around them. This ripple travels close to the speed of light, not because electrons are racing through the metal, but because fields in space are adjusting. The electrons respond to those fields. They drift slightly, nudging the charges beside them, but they are not the main carriers of energy. They are participants in a much larger structure. What you call electricity is not confined to the wire. It is a pattern of electric and magnetic fields surrounding it, and those fields extend outward into space, shaping how energy moves through the circuit. The wire does not contain electricity. It guides the fields that make electricity possible, where the energy actually travels. By now, your attention has probably shifted. At first, you were looking at the electrons, then the wires, but the real story of electricity is not centered on either of those. It lives in the fields surrounding the circuit. This is the part that almost every simple explanation hides. When a battery powers a circuit, energy does not crawl through the copper wire carried by drifting electrons. The energy moves through the space around the wire. This idea sounds strange because we are used to thinking of empty space as inactive. But electromagnetic theory says the opposite. Space around electrical systems is full of structured fields, electric fields and magnetic fields that interact with each other. When current flows, these fields form a pattern around the conductor. An electric field runs along the wire. A magnetic field circles around it. Together, these fields create a flow of energy moving through space. Physicists describe this flow with something called the Poynting vector. but you do not need the mathematics to grasp the idea. Imagine energy sliding along the outside of the wire, guided by the fields that surround it. The copper does not carry the energy like a pipe carries water. The copper simply shapes the fields so the energy flows where we want it to go. In a simple circuit, the energy travels from the battery through the electromagnetic fields surrounding the wires, and then into the device like a light bulb or motor, where those fields interact with charges inside the device. The wire is not the highway for energy. It is more like the guardrail that keeps the fields organized. Without the wire, the fields would spread out in all directions. With the wire present, the fields align and guide the energy precisely along the path of the circuit. So when the light bulb turns on, the energy powering it did not travel inside the metal from the switch. It flowed through the electromagnetic field surrounding the wire and into the bulb. The electrons inside the wire barely drifted, but the fields carried the energy. The strange role of the wire. By now, the wire looks different. At the beginning, you imagined it as the main pathway for electricity, the tunnel through which energy traveled from one place to another, but the closer you look, the less that picture survives. The electrons inside the wire drift slowly. The energy moves through electromagnetic fields outside the wire. So what is the wire actually doing? It is not transporting energy the way a pipe transports water. Instead, the wire acts like a guide, a boundary that shapes the electric and magnetic fields around it. Think about the rails of a train track. The rails do not push the train forward. The engine does that, but the rails guide the motion so the train moves in a specific direction instead of wandering across the landscape. The wire plays a similar role for electromagnetic fields. When a battery creates a difference in electric potential, it establishes an electric field along the circuit. As charges begin to drift, a magnetic field appears around the conductor. Together, these fields create a structured pathway through space. The wire keeps those fields aligned. Without the wire, the fields would spread outward in every direction. Energy would disperse into space instead of arriving neatly at a device like a lamp or motor. The conductor channels the pattern. It holds the electric field in place. It shapes the magnetic field around it. And together, those fields carry energy along the circuit. This is why electricity can move through many different materials. Copper works well because electrons can shift easily inside it, allowing the fields to stabilize quickly. But the energy itself is not trapped inside the metal. It flows through the structured field surrounding it. The wire is not the main actor. It is the stage manager quietly arranging the conditions that allow the real phenomenon, the electromagnetic field, to move energy where we want it to go. Electricity without flow. At the beginning, electricity looked simple, a current moving through a wire. Electrons rushing from one place to another. Energy delivered the way water moves through a pipe. That picture felt natural, but each step of the journey quietly removed parts of it. Electrons drift slowly, far too slowly to explain how quickly circuits respond. The light turns on almost instantly, long before any electron could travel the length of the wire. Electric and magnetic fields appear around the conductor, spreading through space as the circuit changes, and the energy itself moves through those fields, not inside the metal. The wire, which once seemed like the main pathway, turns out to be something more subtle. A guide, a structure that shapes how electromagnetic fields form and interact. Electricity, in the deeper sense, is not a substance flowing through matter. It is a pattern, a dynamic structure of fields interacting with charges. The electrons matter. They respond to the fields, shifting slightly and allowing the pattern to propagate, but they are not the cargo carriers you imagined. The energy that lights your home, powers your computer, or runs a city's electrical grid moves through the space surrounding the wires, carried by electromagnetic fields shaped by the conductors. The current you measure is only part of the story. The real movement is happening in the invisible architecture around it. And once you see electricity this way, to the old picture, the water flowing through pipes starts to feel strangely small, because electricity is not a fluid moving through metal. It is the behavior of fields spreading through space, guided by matter, and revealing that what we call empty space is anything but empty. It is active, structured, and capable of carrying energy across the world without a single drop ever flowing through a pipe.